Hi, everyone. Thanks so much for having me. My name is Kelsey Doerksen. I just finished my PhD at Oxford in the Autonomous Intelligent Machines and Systems program, which is based in computer science. So my PhD is in essentially geospatial AI. And now I'm a joint postdoc at ASU with Dr. Hannah Kerner and also at the University of Cape Town in the Climate Risk Lab with Dr. Chris Trizzo. So I spend time between the two institutions working on essentially like geospatial AI applications to food security, and then also just like fundamental geospatial AI research, which is what EarthShift is a part of. So I think we all know that foundation models have seen what feels like quite an exponential growth in development in the recent years. And with that has become sort of a kind of specific genre of what I'm interested in, which is, of course, geospatial foundation models. And these are specifically useful, of course, for science and sustainability applications, including like climate monitoring, deforestation, land cover change, crop yield estimation, biodiversity mapping, disaster response. The list goes on and continues. And so we built EarthShift with the idea to quantify robustness of these models to help practitioners and folks interested in using these types of models in their own work kind of select and understand how well the different models are for their specific applications. So I'm going to start with just like a quick primer to GFMs or geospatial foundation models. I think probably folks part of the working group have worked with them or at least have some exposure, but just so that everyone's on the same page, we know that a foundation model is a pre-trained model that's typically trained using self-supervision with unlabeled data, and it extracts generic features useful for a wide variety of downstream tasks. So this could be, again, like crop yield estimation, for example, or it could be climate change applications. The output of these foundation models is a feature representation or an embedding, and it's not necessarily the final task answer, right? We're not getting like predicted yield or crop type, but this requires adaptation to a specific task like fine tuning. But the idea behind these models and sort of the purpose of why they're so popular is that they're supposedly quite good at better generalization than traditional models, and you need fewer labels compared to fully supervised approaches, which is really great when you're working in contexts where you have very few labels. So there are kind of like the two main ways to interface with these types of models. We can use them as like a frozen feature extractor where we're using those embeddings like Alpha Earth, for example, which has embeddings hosted on Google Earth Engine. Then you can add another layer after that embedding layer that predicts the downstream task, even like a simple random forest or linear probe, something like that. Or we could fully fine tune the foundation model, which is a lot more computationally heavy. And then you can then add that final linear layer as well. So this is a little bit more computationally intensive, but if you have more of a larger data set to fine tune your model with, that's another option. But in general, the sort of like TLDR from this is that embeddings are cheaper, but generally less performant, where fine-tuning is more expensive, but you can get a little bit more juice out of these types of models. And why do we care about these? Why are these super helpful? Why is everyone like really excited about these types of models? So since the pre-training data is unlabeled, the model can learn from a much larger data set with greater geographic and temporal coverage than would be available in a labeled data set. So in my case, I work a lot in contexts within the African continent where there isn't a lot of labeled data for different applications. I'm focused more on food security. So the idea is maybe we could use these geospatial foundation models to fine tune them or use their backbones to be able to generate models for a variety of different tasks. The idea is it's better generalization to unseen places and fewer labels. And this is just an example of the OML Earth Foundation Model pre-training data set, just so you get an idea of what folks refer to when they say, global or like full generalization across the planet. I will say, I think folks that work in the geospatial AI world know this, that any model I think that claims to have global coverage is of course usually concentrated very heavily in North America and Europe, and there's much more sparsity or less density of labeled data in other sections of the world or other regions of the world. So when we claim these models are trained with global available data, I would say there still is of course a disproportionate amount of the data is from what we refer to sometimes as the global north. So this can cause some hiccups in downstream training. And there's many things to consider when we're choosing geospatial foundation models or which one you want to use for your different application. Things like ease of use, especially if you're working with perhaps maybe like less technical audiences or folks. I work with folks in more like governmental institutions who frankly don't have the time to like code up and, fine tune the foundation model themselves. They really want like as simple as an interface as possible. So this is something really to consider, as well as cost of use. Things like how much is it going to cost for inference in terms of compute, storage of these embeddings. These embeddings can be like quite huge, especially if you're looking at a very large AOI, your application requirements, and then of course, data coverage. At the time of making this slide, there was around like 75 plus models on the awesome, I think it's called like awesome remote sensing GitHub link, but I'm sure there's like 100 plus now of foundation models, and it's continuously growing. So it's kind of, there's a lot of factors to consider which one should you choose for your use case. But the big problem with these models is that they're quite brittle, and current benchmarks test in distribution generalization of these models, but real deployment, of course, requires handling new time periods, geographies, scales, and sensors. So where we might have contexts like, let's say, in biodiversity monitoring or deforestation, if the model performs really well in one geography, it might totally fail in another geography. And so the goal of EarthShift and our research is to actually quantify the robustness of these models and to evaluate in distribution or out of distribution performance, not in isolation, but to measure the robustness across distribution shifts. So I'll get to what we mean by in distribution and out of distribution in the following slides. But first, I'll just highlight kind of what the goal of EarthShift was and what really our motivation behind it is. So the first was to understand like how robust are GFMs to realistic distribution shifts that are encountered in remote sensing applications. Are geospatial foundation models that are pre-trained on Earth observation data more robust than standard vision foundation models? There's a lot of work and effort being put into creating these models and using satellite products and data sets into pre-training these large models, and a lot of compute goes into this. But how do they do to standard ImageNet pre-trained models? We also wanted to look at how our pre-trained GFMs in terms of robustness to fully supervised models with randomized weights. Ideally, we're putting a lot of effort into pre-training these models, so hopefully they should be doing better than kind of randomly initialized weights on a ResNet. But we wanted to make sure that this is actually the case. And then we also wanted to look at fine-tuning strategy and how this impacts robustness in terms of full fine-tuning or using that frozen backbone. And just from like an AI and sustainability lens, we know that models that fail under distribution shifts are a sustainability problem, because a model trained on data from one region or sensor and then deployed to another can produce like confident but wrong land cover maps or yield forecasts or change detection outputs, which can be a really big problem in real world applications. And so I want to take a few minutes to really go through the distribution shifts that are supported by EarthShift, because I think this is really kind of like the meat and one of the most important things about the paper itself. We've defined 5 different distribution shifts here, and I'll go through each one. And I refer to often in this talk in distribution and out of distribution, or ID and OOD. So what I mean by in distribution is test samples from the same distribution as the fine-tuning set, and out of distribution, or OOD, is test samples that are shifted from the in distribution data in some way. So let's start with scale shift. Let's just focus on that. So this is dataset pairings, whereby the datasets in question cover the same like land cover types or classification types. If it's a classification dataset, they have the same geographic coverage, temporal coverage, but they have differences in their image resolution. So there is a difference between the actual spatial resolution of each dataset in the ID and OOD. So this could be something like maybe 0.2 meters per pixel is the ID set, and the OOD set could be 30 meters per pixel. And how does the model perform in cases where it's fine-tuned on a finer resolution or a coarser resolution than another? We also have temporal shift, and we use fields of the world data set for this, which is a global data set of field level boundaries produced by Hannah Kerner as well as Taylor Geospatial. And we look at two different types of temporal shifts. We look at it over season. So the beginning of the season, we call window A. And then the end of the season, or like when the crops are harvested, we call that window B. So we look at, how well does the model perform when it's looking at delineating those field level boundaries. And then we also look at that from year to year as well. So these are just examples from South Africa and Germany listed on the slide here, where we look at, how does the model perform on the ID set from 2018 in Germany, and how does it do on the OOD set in 2019 in Germany. So you can see very small changes in sort of like the actual visual image there, where there's this section in this bottom right corner that's a bit lighter or more brown in 2019 versus 2018. And how do models deal with that? We actually look at all of the countries within fields of the world, but I just took a subset to show you the a visual representation. And then we also look at location shift. So this is, again, using fields of the world. And we look at a different set of countries where we fine tune our ID set is on Germany. And then we do a couple different countries as our OOD sets. So Cambodia, which looks very geographically different from Germany in terms of very much smaller sort of little parquets or field level boundaries. And then we also have an OOD set of Denmark, which is a little bit more similar to Germany in that it's much larger field boundaries than what we see in Germany. So how does the models deal with that? Then we also look at sensor shifts. So these are different spectral characteristics or modalities. So we look at, we fine tune on Sentinel 2 and our OOD is Sentinel 1. How do the models perform in that case? And we also look at just shifting one of the sensor bands in the M-Euro set data set. So we take an RGB image as our images as our ID set, and then we remove, for example, the G band and replace it with another band in the OOD set and see, how does the model perform in those cases. And then the final final shift that we include is data source shift or data set to data set shift. So in this case, the data sets in question are from different authors, but they cover the same land cover types or classifications within the data set. They cover the same temporal coverage, geographic coverage, same resolution. The only difference is that they are from different authors. So there's two different data sets, the Deep Globe and DFC 2022. They both have things like, land, let's say it's water bodies or forest or built up environments, things like that. But it's just for two different applications from two different papers. So in theory, you should think that there shouldn't be any sort of substantial performance drop for these models since the data sets are pretty much the same, but we explore this as well out of interest. So those are the shifts, and this is a table from the paper. I won't go into too much detail about that because I think folks can look at that on their own time and just in the interest of time and having time to discuss results. But these are the ones that we include. We have 11 test cases across the 5 shift types. And these are the models that are currently supported by EarthShift. So we have 8 Geospatial Foundation models listed there: DOFA, Chroma, Clay, Prithvi V2, Terra FM, Dino V3, pre-trained on its satellite data set, Galileo, and TerraMind. Then we also include generic vision foundation models. So this is ResNet 50, VIT, and CLIP that's pre-trained on ImageNet for this cross-domain comparison that we're interested in. Then we also include these fully supervised baselines. So these are randomly initialized ResNet 50 and VIT to then evaluate the sort of benefit of pre-training. We run around 10,000 plus experiments across these 13 models. We do 5 seeds each. So we report these results in the paper. You can see in the extended results as well, the standard deviation across the runs. And we do the 2 fine-tuning protocols. So we do full fine-tuning where all the parameters of the models are updated. And then we do that frozen backbone where only task-specific heads are trained. So our goal is not to maximize the performance of each model. We just do linear probing, very simple linear classifier or linear or a decoder, depending on the task, if it's classification or segmentation at the end of that frozen backbone. And then we just list here a table showing the different learning techniques between the models and also their number of parameters. So we use, for example, in Dino V3, I believe we use its like small or tiny version. I forget the name off the top of my head, but we try to choose models that are relatively similar in parameter size, so that it's as apples to apples comparison as possible. Dino V3, this was the smallest one, for example, but these are sort of the main model parameters. Okay, and then before jumping into the results, I want to first discuss like how we actually quantify robustness of these models. And we do that through a methodology called effective robustness. And this is from the Measuring Robustness to Natural Distribution Shifts in Image Classification Torrey paper, where they looked at ImageNet V1 to V2 performance drop, and they saw that ImageNet models drop greater than 10% when evaluated on ImageNet V2, which was quite surprising since visually they look quite the same to the human eye. So EarthShift uses effective robustness framework so that we can measure OOD performance relative to in-distribution performance capability. So we have this equation here, rho F, where we have the out of distribution score minus a in-distribution score that's multiplied by the parameter beta, where beta is the baseline fit on the ID versus OOD points. I think it'll become a little bit more clear once you see actually the graphs themselves as well. So the idea is that we want to disentangle true robustness from overall model capability, but we also report just like absolute in-distribution scores and out-of-distribution scores and like an overall performance delta in terms of like absolute performance drop. And just to kind of further support why we think that this is a good way to quantify robustness of these models. Just like a really quick use case, if you consider the following three models and their scores. So let's take model A has an ID score of 90% and OOD score of 70%. That has a 20% delta or 20% drop in performance. If you look at model B, its ID score is 15% and its OOD score is 10%. That's only a 5% drop in performance. So if you're looking at just delta, performance delta, that would suggest that maybe model B is like more robust and a better choice than model A, but in reality, model B is just very bad, right? It's like it's performing very poorly on both data sets. So we want to look at this performance relative to the in-distribution performance capability so that we're able to kind of have a better way to look at the effective robustness itself. And with that, I'm going to jump right into results. There's lots of plots, but I'll go through each of them individually as well, and then leave time for discussion. So the main takeaway, the spoiler, is that essentially Geospatial Foundation models show no robustness advantage over standard vision foundation models or randomly initialized models across all shifts. This is showing the frozen backbone type, and I'll go into each one of these plots as well. So I know it's a little bit overwhelming to have all of them on the same slide, but just so you're aware for the kind of like the following slides, you'll see each color, so each point color represents a model, and then each shape of the points represents a different task or shift type. So we have the temporal shifts, sensor, scale, geographic, and source. And sort of the main takeaway from the results that we've seen so far is that the GFMs don't show any advantage over generic vision foundation models or the random baselines, that we have a sort of like mean effective robustness across all shifts. These models are kind of clustering at this baseline or are below, which shows that the model performance OOD is quite drops quite significantly, and you'll also see this in the absolute deltas in the following slides. And we see the same thing as well for the full fine-tuning setup too. So irregardless of fine-tuning strategy, full fine-tuning or frozen backbone, we're seeing quite significant performance drops and very little to no robustness to these different shifts. So let's look at first a temporal shift, which is, I would say, one of the best examples of robustness of the shifts that we show. So we can see that there's, high robustness, I guess, is relative to the robustness values of the other shifts that we show. But relatively speaking, the models perform pretty okay when we're looking at temporal shifts. And this kind of makes sense when you think about the data sets that we use. We use fields of the world, like I mentioned, and we're looking at like season to season temporal shifts or even year to year. And when you think about the context of like agricultural field boundaries, these aren't changing very dramatically between years. Like now I'm not an agricultural expert or a farmer, but I know that the farm shapes are not changing very dramatically between seasons or at the beginning of the season versus the end of the season. So the models aren't struggling too much in terms of that ID versus OOD performance. But there still is actually like quite a interesting drop that we can see when these models are actually below this dark fitted line there. Now, when we look at sensor shifts, this is almost the other end of the spectrum, the extreme. We see that these are the least robust to sensor shift. There's the largest degradation between ID and OOD performance, and thereby effective robustness. I mean, this makes sense when we think about that there is kind of like a fundamental modality mismatch between the sensor shifts that we're looking at. So we look at, for example, the kind of hexagon here is RGB to RGE1, where we're substituting that one sensor band, versus when we do Sentinel-2 to Sentinel-1 shifts and SenFloods-1 or the big EarthNet data sets, we're seeing like pretty significant drops in performance. But again, this kind of makes sense when you think about, Sentinel-2 is very dramatically different than Sentinel-1 data. So if you're fine-tuning your model on this Sentinel-2 data, and testing on that Sentinel-1, it's not too surprising that it's having quite significant drops. So we're not overall shocked by these results, but it's still quite dramatic that we've seen. Robustness to geographic shift depends on shift severity that we find in the data sets or the data pairs that we've provided in EarthShift. So we have, like I mentioned before, we're using fields of the world. We have Germany as our ID set, and then Cambodia and Denmark are the OOD sets respectively. So Cambodia, those shapes are the down pointing triangles and the OOD set. And for Denmark, those are the sort of sideways or right pointing triangles. And this is this line of best fit between these points is basically almost dividing them, where we can see that the models are performing much better on the shift from Germany to Denmark than they are from the shift from Germany to Cambodia. But this makes sense when we visually look at it, right? It's a much harder problem or more difficult task for the models to delineate field boundaries from Cambodia, for example, when you're training on like such a large field boundaries, relatively speaking, on Germany, whereas Denmark is a little bit more similar. So we're seeing a better distributional robustness in these cases. But again, this is only 2 examples, and in order to fully have, this is something we talk about in the future work of the paper in general. Of course, we're not covering every single geographic shift, and there are many different types of applications. But in this case, we've seen that the geographic shift robustness depends on this sort of severity. And then even on similar data sets, we see that performance can drop on the order of 30%. And this is similar to what, again, the Tory paper found in their ImageNet V1 to V2, that even monitoring identical data sets is important. We would think that it should be kind of apples to apples comparison, especially because we do have the same classes, we have the same resolution, temporal coverage, geographic coverage, but we see even in those cases that the models are showing distributional or a lack of distributional robustness in these cases, which is pretty shocking and surprising. And then there's a lot of numbers on this slide. It's quite a busy table, so I don't want to have folks too overwhelmed and focus really on the numbers. I think the main takeaway from this is that we've shown that generic vision models and random baselines have greater than or equal to effective robustness than these geospatial foundation models. So what we're reporting here is the per model ranking of effective distribution shift per shift type. So that row value per shift types of sensor, geographic, temporal, scale, and source shift. And we can see that in both the full fine tuning and frozen backbone settings, the ResNet 50 pre-trained on ImageNet actually has the best average effective robustness across all those tasks than the geospatial foundation models. And even the ResNet 50 initialized on random weights is in the top 4 in full fine tuning and the second best when it's ranked in the frozen backbone. So it's pretty shocking to see that with all of the effort that's being put into pre-training these models and creating these global data sets of Earth observation data, in terms of an effective robustness approach, they're actually not performing as well as the simply ImageNet pre-trained models. And you can see again in the paper that's linked at the end of this presentation as well. You can see every single absolute score for OOD and ID performance in the tables to look at each one more individually. These are averaged results across the seeds. And so I wanted to show a few more slides of results as well before we talk about like the main takeaways. So this is looking at now absolute performance. So what we're plotting on the y-axis is average performance gap. So this is the ID score minus the OOD score. So the larger the bar, the worse the models are performing on their OOD set. So we want the bars to be like as small as possible. You're seeing on this Fields of the World seasonal all that refers to the temporal shift from the beginning to the end of season across all the countries. It's just so small in the results that it didn't plot relative to the rest of the values and the rest of the bars in the graph. So it's not zero completely, but it's quite close. But what we can see here is that overall the sensor shifts again are performing the worst in terms of absolute performance drop. We've color coded the bars as well. So the green represents the Geospatial Foundation models in their two fine-tuning and full fine-tuning setups. Orange refers to the Vision Foundation models. So these are the ones that are pre-trained on ImageNet. And then the blue is related to the fully supervised. So this is using the randomly initialized weights. So we can see that the GFMs have similar or sometimes worse robustness when we're just looking at absolute performance drops, where we have sensor as like the absolute worst. Our temporal shifts, the models are actually like fairly robust. There's like slight drops in the South Africa seasonal case, but overall it's not too bad. And in that, even in the spatial, which is like the difference between, again, those image resolutions, we have pretty significant drops between the model types. And then we also looked at, in terms of grouping the results by their fine-tuning strategy. So full fine-tuning is, apologies, the coloring on this text will be a little confusing. So full fine-tuning is blue, and the frozen backbone or just using like a linear head is in pink. We can see that the model robustness doesn't improve or actually worsens when the encoders are fine-tuned. So whereas we have maybe achieving higher in-distribution scores and full fine-tuning, it actually leads to worse OOD generalization. And the frozen models trained with a linear task head exhibit higher distributional robustness. So again, this refers to the larger the bar, the worse the performance drop is, or like the greater the performance drop between ID and OOD score. So you want the bars to be as small as possible. So we can see for the blue bars, which are full fine-tuning, they're always consistently higher than fine-tuning just the head, except for the case of this little anomaly in South African seasonal. And then just to have a nice figure where every single thing is plotted on the same thing. I know this is not a good way to get specific takeaways, but we wanted to look at, like, if we plot every single thing and do a line of best fit, how do the models performing overall, or like, can we see like clusters or trends? So again, how these are grouped is the colors represent the different models, and then the tasks are represented by different shapes. And we've grouped the shapes according to their shift type. So for example, the triangles are all temporal shifts, and you can see that they're pretty good in terms of the out of distribution versus in distribution performance. There isn't like any real big drop, which is what we've seen relative to their effective robustness as well. Whereas we have like much bigger drops in, for example, like the Germany to Cambodia, the in distribution performance versus out of distribution performance. There's quite a big drop there. And overall, we can see that there's like generally a trend of shifting to the right, or like a higher in distribution performance with those full fine tuning, but this doesn't actually help robustness at all. And then I believe this is the last plot that you have to digest out of all of the results. We wanted to look at too, from just like an AI and sustainability lens, how does model size correlate with performance? Is bigger really better? Or can you get away with similar results, or at least from an effective robustness perspective? Does like smaller models still perform pretty well as compared to bigger models? And we found that model size actually doesn't correlate with performance. We show that there's no correlation between the GFM size and the performance delta. So again, that's that difference between the ID and OOD score. And so, essentially the main takeaway from this is that you can use, basically any of these models in terms of their parameter size. One is not distinctly better than the other. So for example, in Dino V3's case, where it's around 300 million parameters, its performance delta in terms of its drop between ID and OOD performance is quite similar to CLIP, which I think is on the order of less than 100 million, but I'd have to check on that table that I shared at the beginning. Okay, so there was a lot of results, a lot of plots, but just to like summarize the main key takeaways before I get into like questions and discussions. The things that we found in EarthShift as it stands, the Geospatial Foundation Models are equivalent or sometimes worse to vision foundation models in terms of robustness. So the ImageNet pre-trained models show similar and sometimes better distributional robustness across all of these tasks. We also show that the GFMs don't necessarily outperform supervised models, even with random weights. And this really challenges the core premise of foundation models. The whole purpose is pre-training, and like I think the research field of pre-training strategies is still like very open, and there's a lot of unanswered questions. And I think EarthShift has even created more questions as opposed to solutions, which is kind of the purpose of EarthShift, is to sort of challenge assumptions that are made in pre-training strategies or in the idea of foundation models at all. We saw that full fine-tuning hurts robustness, which was also consistent, I believe, with the Tory paper. And we've shown, though, that temporal shifts are generally speaking the exception. With the data sets that we've provided in EarthShift, we see only like minimal performance delta drops. And again, sort of thinking about this AI and sustainability lens, we have on the order of billions spent on compute across all of these models, but we're not really getting robustness return on interest. And so it really begs the question of, are we investing in the correct things when building these types of models, and what are ways that we can improve robustness? So in conclusion, EarthShift is the first comprehensive benchmark for measuring distributional robustness in SAT-ML or satellite machine learning contexts. It reveals a critical gap. Current models that we've shown have around 20% OD degradation on average, and domain-specific pre-training has conferred no robustness advantage. Of course, like limitations and call-outs, this is a non-exhaustive list of GFMs. There's always room for more. Something that I learned like as a practitioner myself, as I mentioned at the beginning, my PhD is in AI, so I'm like very comfortable with coding and development, and even it was quite a challenge for myself to interface with all of these GFMs and fine-tune them and learn about, even though if their weights are available online, like there's a lot of like tips and tricks, and it's not as straightforward as I think a lot of models claim to be able to be, and like as easy as it may seem when in papers that claim that you can just like download the weights and run them. There are a lot of caveats, so that is just something to think about as well. And hopefully we've set up the infrastructure within EarthShift, and the code is all open source, that you can see exactly like how we fine-tune fine-tune strategies, how we load the data, all of these things. So hopefully folks can use it, even if you don't want to use EarthShift for robustness perspective. If you just want to fine tune one of these models, you can see how we do that in the GitHub repo itself. We always want to add additional data sets to support other shifts. So if like folks joining me today, or if anyone has suggestions, and I would love for folks to reach out if there are other shifts or data set pairings that they'd be curious or interested to see in future iterations of EarthShift, in terms of the data sets of the current shifts, but also additional shifts that are common to remote sensing. Again, this is a non-exhaustive list. But the key takeaway is that we think that future research in the field of GFM should prioritize distributional robustness and not just in distribution performance. But again, all of the code and data sets and onboarding instructions for how to interface with the tool is publicly released. And you can find all of the information about the EarthShift project, our project website, the archive paper, as well as the code and links to the data as well. All the data we used is open source too, via that QR code. And I'd be happy to take any questions or any comments at this time.
That was awesome. Thank you so much. Really, really rich presentation. We have like 15 minutes. Feel free to just raise your hand if you've got questions, or just hop on the mic. I want to leave it open for folks. Sujit, over to you first.
Hi, Kelsey. So it was a really nice presentation. I really enjoyed it. There were a lot of controversial points that you raised. I find them very critical, but I have several questions actually, based on the evaluation that you did. And I fundamentally don't agree with most of the evaluation that you have. The reason being, like the premise of foundation model, right? The way you explained it. The premise of foundation model is not only on the basis of like, your sensor shift or something like that. It's fundamentally when you try to train these models or fine tune these models, you require two things as a fundamental thing that you observe, right? One is less number of fine tuning, so you require less number of samples, and then you require less number of potential iteration. Did you do any test with that one? So you provided ResNet random weights with this, let's say 100 samples only, and you gave these models 100 samples only, and then try to evaluate that, okay, which one converged faster or something like that?
Yeah, we did. We reported more deep, like technical details in the appendix of the paper as well. So we also do like learning rate sweeps to choose the best learning rate across, I believe it was 9
hyperparameter selection. Yes, I looked at that I read your paper. I'm like, while going through the talk, I was going through the paper as well, and I looked at it. So, like, I feel like that was somewhere it's ill-posed, and also I feel like a lot of problem are ill-posed, because calling sensor shift out of distribution is a very ill-posed problem, right? Because you're asking, for example, like one thing also you said is feature to finer versus coarse, that I made a note of. So 0.2 meters to 30 meter. It's a problem that is completely wrong to be asked to a model. If I'm looking at a model at a 30 meter resolution, and you ask a model to do an outer distribution shift to 0.2 meters, this problem is completely ill-posed because the features that you're looking at 0.2 meters won't ever be visible to 30 meters. So there is no possibility of a distribution shift. You're asking the model to relearn these things. And then the weights that you have in these models are actually equivalent to random weights. So fundamentally, whatever role is happening there is based on the architecture. It has nothing to do with the data set, nothing to do with learning. Similarly, when you do the sensor shift, you evaluate, let's say, an optical model on SAR data. It's not an out of distribution problem. It's a mischaracterization of the problem, because you're asking that fundamentally they're two different modalities, right? Optical and SAR doesn't have anything common. If you can derive SAR out of optical and optical, out of SAR, it's not so vice versa, then you're asking that there's no need for these satellites or these sensors fundamentally. So sensor shift is a multispectral optical imagery to C-band SAR. They're fundamentally different. It's not an out of distribution. So feature space will not have any structure. So whether you do fine tuning, you call it fine tuning or frozen backbone, you're fundamentally applying a learned kernel on something else, an optimized kernel on something else to a completely different problem, right? So it's calling this a distribution shift. I feel like it's a mischaracterization of the problem. That one. And same thing that you quoted, I think, Tauri et al. Related to the distribution robustness thing, right? So when you change or replace a band with B04 with something else, you're changing the physical quantity that you're measuring for one channel. So whether one model handles this is about spectral interpolation capacity and not distribution robustness. So again, this is something, and that's why when you look at your results, you see something reasonable on, let's say, temporal or something where a model has actually seen that or understand a spectrum. But you move across sensor, you move across band, you change certain things. It doesn't perform well because that is not an out of distribution problem. It is something completely multi-model transfer, right? It's a modality transfer that is happening. And for that, I can choose any model technically. I'm an average computer scientist, but I can pick up, let's say, one model and I can add a couple of injection mechanism and I can make the model learn that. But that is the capability of the architecture. It has nothing to do with the distribution data set or something like that. So that's what I feel like, but I'm open to what you think.
Oh, did you want to add anything, Tim?
Yeah, I was just going to hop in and I had a thought maybe around like the study design for essentially around the frozen models that are inherently multimodal to begin with, and sort of breaking that analysis, like I'm thinking clay and Terramine as like a grouping, and maybe Prithvi, HLS, and other modalities as separate. I wonder if and I'll dig through your paper too to just sort of see keeping those as like separate challenges. I think that's an interesting element, because I was trying to writing down notes too. I'm like, on the architecture side, sort of how is that divvied up? And I think that's maybe what Sujit was getting at as well. But that's a really interesting question. And again, I left your talk. I want to give it back over to you. We got still 10 minutes, so I don't want to eat up too much time.
Yeah, no worries. I mean, this was like a long part of the benchmark, or the tool itself is like defining what these distribution shifts are. I mean, the sensor shift, we took inspiration from GeoCrossbench, which does shifts between, like, their identification of what shifts are between like different band types. I don't know if you've read this paper itself. Like we were thinking more so like, look, I used to be a satellite operator, so I'm well familiar with satellite data from that perspective too, and also from like on-orbit anomalies. So if you think of the case, let's say for the sensor shift one, you have RGB and then you have another band. Like, you know, what happens if one of the sensors is broken on the satellite and you only have this data? Is all of that data garbage now? That's going to cost you like tens of millions of dollars, or can you use the models that you already have pre-trained on the data that you've been pre-training on, that when the sensors were available? Like this is like one operational perspective from like a SatOps world. I do agree that like the Sentinel 2 to Sentinel 1 shift, like it's super difficult. Like that's why we wanted to include it. And actually we got initial feedback from folks at CVPR to actually add these shifts, like these Sentinel 2 to Sentinel 1 shifts. That was one of the biggest feedback we got at the initial iterations of the paper from the community, because originally we only had like either like a replacement of like RGB to RGB plus NIR, for example. And it was the feedback from the community was like, oh, well, what about if you do Sentinel 2 to Sentinel 1? Like how do the models fare? So this was like direct feedback from the community that was implemented into EarthShift. I'm not defending every single shift like that. You know, there are better representations or not, but fundamentally, like the question is like, how do these models do across shifts that you might encounter in remote sensing? And we know that like different satellites have different sensors, so you know, how do they do in this case? But I do agree, like this is like super hard for the models to do. You don't expect them.
It's not hard.
To do well.
I feel like it is completely ill-posed. I'm like, hard is like when I'm trying to do a modality to modality reconstruction, a model can't do that. When you're asking the model to learn completely a different physics, which it never encountered. It's like you train a model on a partial differential equation of Navier-Stokes and you ask the model to solve something completely different partial differential equation. How is it? It's not fundamental shift. It's asking a very different question. I'm like, you got a feedback from them and then you incorporated it. I'm like, I'm just trying to understand, like you can't agree or disagree, right? That's what I'm trying to see. I'm not a remote sensing expert, right? And, but I'm trying to think, if I cannot create, like a human being, right? If you have a mathematical symbolic representation, very simple question I have is, I give you SAR data, I give you optical data. Can you give me a mathematical formulation to convert optical to SAR? If you cannot give me with all the thorough literature that you have in remote sensing, then what you're asking the model is a very wrong question. A model trained only on optical data and asking it to learn or perform on SAR is like, I don't know, maybe you trained something completely on very different data set with very different spectrum and asking to perform something on completely different and calling it out of distribution. It's not distribution. There's nothing related to distribution here. It's completely different feature space. Same thing. For example, in atmospheric dynamics, right? You train a model, let's say on 50 kilometer resolution, and you try to ask the model that, hey, can you look at and perform on 3 kilometer resolution? It's impossible. Until the model can look at the raw data, it cannot understand how to resolve something at that resolution, 3 kilometer, right? Because the features that you're looking at visible, you know, like for example, same thing that you told, 0.2 meters, what you're looking at 0.2 meters won't even be visible in 30 meters. So what model has to do is going to relearn every single thing. And then you compare it with ResNet or anything else, it's fundamentally same platform. It's fundamentally what you're doing is not a shifting or fine tuning. You're fundamentally retraining again. It's all relearning. I call them relearning. You will not have a relearning on situation the model has only RGB components. You can leverage some RGB from here and there. And be like, okay, some spectrum matches, you will get some jump start. But it is fundamentally wrong question to ask or begin with or validate against.
Okay, I would ask you then, what's a shift you would do? Because I'm getting lots of feedback and I'm like super happy to.
Sensor shift is something I won't do.
Yeah.
Like, I totally agree with your temporal shift. I totally agree with your geographical shift. It's completely perfect. Scale shift to a certain extent makes sense. For example, a model that has looked at, let's say, 10 meter and 30 meter resolution, you can ask them to work on any single thing. But the moment, I'm like other people from remote sensing background can assert that I'm not a remote sensing person, but I'm trying to think from mathematics perspective, right? Only purely mathematics is, when I train a model on a specific distribution or something nearby, I can do that. Sensor shift is not one of them. I train a model on optical asked to perform a SAR. I'm asking somebody to perform, a person who, let's say, who knows how to play a violin and ask them to perform same way on piano. Just because both of them come in the music, it doesn't mean they're transferable, right? So that's one thing. Scale, completely, scale is at a certain extent I can do that, which is a completely mixture of input data. Geography, totally agree. that should be something that if you're training a global model, then if you have data set from USA, England, or India, you should be able to transfer that across, and you should have good performance, and you should be doing better than ResNet or random weights ResNet. If you're not doing, then maybe I would look at the pre-training data set that model has used and probably have it more changing of the data set, right? That part I agree to that one. But other than that, I think it feels like you're testing these models against something that was never to be tested against. So putting them in a very, very hard categorization and then calling them like it's a whole resource is a waste of money for training these models. But every model has improved by looking at these weaknesses. So that's why initially you had optical model, then people moved to multi-models of mixing optical and SAR, then you got Galileo, which is mixing optical, SAR, and a couple of ERA 5 components. So they have been added, and this is how I think this field has evolved, right? So when you create a data set and benchmark and call it like based on these parameters, I feel like then this is an overstretch of a claim. Again, that's nothing to be on that side, but you can, I'm like, this is what I will ask you to ask your question yourself, because you are an AI person, right? I think that you're doing a PhD in AI. So you should ask the question mathematically to yourself that if you design a model, do you expect it to actually solve all the problem? Or is it the distribution problem? So calling a distribution shift or something, modality robustness is a different problem. It's a well-studied problem. We do that all the time, modality to modality construction and other stuff. It's not an auto distribution problem. That's one of my fundamental problem with that paper was actually.
Yeah, no, and I appreciate the feedback. Like, I'll be honest, like the reason we put in Sentinel 2 to Sentinel 1 shift was direct feedback from like the geospatial AI community that asked us to put it in. So like it is direct feedback from users of Geospatial Foundation Models that are interested.
Yeah, I'll put that in, but I'll probably not report the results on the optical data. I'm like, if they want it, I'm like, people can want a lot of things, any AI community, but if you are working on the AI, I'm like, if you're trying to explain them, then you have to defend the work as well, that it is not meaningful. It is meaningful in the case when the model has seen, for example, like Terramine, right? I know this is a multi-model model and it has seen SAR and optical. You can put that across that test. But you put it to some other models which have never seen SAR in their whole training paradigm and then test on the same thing. You're fundamentally is comparing VIT to a ResNet. That's what you're doing. And that's what you actually, your results shows as well. You're not doing something better than ResNet because you have random weights. It's fundamentally those weights are random to that modality as well.
Yeah, I was just going to hop in and say, I know we only have 2 minutes left. I know this is a robust conversation. This is like, I think your paper is going to be like, this working group especially is going to be really engaged with it because there's people on our side who are really wanting to like dive into these models and more, and they're trying to understand which one's the best one and why. And I think that topic of like grouping models that have trained with modalities, different modalities, could be a way to slice this argument up as well. Because I think the majority of this conversation is really around like sensor shifting. That has been the major conversation, but it seemed like, you know, some of these other designs are like very in line with sort of where we should be thinking about benchmarking. So kudos, I think it's really nice. One thing, and I don't want to eat up all the time because I know there's like other people on the line. I really liked your figure. I wrote down on my notes pink and blue, but it was fine tuning versus full training. That's a really interesting thing. I also think for our group, which is purely more around the applications, where do they spend their energy? Where do they do their work? I think that's a big question for us because if you take these models outright and just use them, that's some work, right? Versus spending all your energy in the fine-tuning process. And like, how do you really dial in? And I found that to be really, really telling. I know this stems back to the larger conversation around the validity of the ODD and ID and these different pots of the analysis, but that was really interesting. And I would love to sort of even explore more into that. So I don't know if you've got additional thoughts just on that topick, because I know our working group is going to look at that chart and be like, all right, how do I sub-select and spend my energy and my compute dollars in the right way as well? So back over to you, Kelsey.
Yeah, totally. I mean, this caused us a lot of heartache. The compute, like the amount of compute was pretty crazy. I think my fair share score, which is like a fair compute score that you have at ASU, is like 0.001 out of 1 or something really, really bad because of this project from just fine tuning so much. Yeah, I mean, even in the applications, I'm working on another project with JPL right now, and we're using embeddings, pre-computed embeddings, or just doing like not full fine tuning for a biodiversity monitoring project. And we found that it's doing like really reasonably well to someone to like another model that was like fully supervised. So this is like, I think I prefer to interface with GFMs in using like the frozen encoder, so you don't have to spend all this compute, because we found it actually doesn't really make that much of a difference, or it's like diminishing returns. I mean, of course, it depends on your application, your user needs and performance needs, that kind of thing. But also just like it takes so long to fully fine tune some of these models. And we chose like the nano or the tiny versions of a lot of these models as well. And it still took like a very significant amount of time, especially when we're doing like learning rate sweeps and multiple seeds, that kind of thing. So I think the frozen backbone is a great way, at least to like quickly test to like what the juice kind of you can get out of these models, which is quite nice.
Wonderful. We're already over time. I feel as though we've cut this discussion short, and you were even kind enough to have a shorter presentation, because this is a really great and typified sort of discussion. I want to say, if you've got anything else you want to present, the floor is wide open. And welcome to have you back. We have open slots in the future too. So I think this is your thinking and perspective, and sort of really interrogating this field is fantastic, because we have all these users on our side that want to sort of explore which is the best one. So this is going to be a really interesting conversation for our working group. So if you've got little milestones or things you want to highlight, the invitation is wide open. We'd love to have you back, because this is a really, really interesting topic. So I'll be sharing out your paper and code base as well. So thank you for all that documentation.
Yeah, thanks so much for having me.
Yeah, thank you. It was a nice presentation. Very nice take.
Agreed, yes. Great job. And thanks, everybody. We'll talk again in 2 weeks. I think we've got a lecture. I'll send it out in the Google group. We've got another great lecture coming up as well. So thanks again, Kelsey. Really, really interesting stuff. And we'll hope to have you back, because this is really, really great. Thanks, everyone.
Thanks all.
Thanks, everybody.
Thanks, everyone.